Hello. So today's video is on matrices, another topic from the syllabus in the same order as given in the syllabus of provided by the CSIR. So first question is from 2019 December. It reads as, if the rank of a n cross n matrix A is m, where m and n are positive integers, with 1 less than or equals to m is less than or equals to n, then the rank of the matrix A square is. So, what do we get? From this equation is that first we should know what is rank of the matrix. So, conceptual thing is rank of the matrix. So, if it is a non-singular matrix means whose determinant is not equals to 0. So for a non-singular matrix, what is rank A? Rank A is the order of the matrix A. Order of the matrix A. Okay, whose determinant is not equals to 0. Okay. Now another thing is, for a singular matrix, what will happen? It will be some order, but less than the order, but less than the actual order of the n. Okay, so for singular matrix, its determinant is A0. So rank A is less than its order, that is n, and rank A is already given to be m. M is less than n, which means that it is a singular matrix. Okay, M is less than n. N cross n matrix is a n cross n matrix of A is a singular matrix. So now, so basically, and defined as rank A is defined as rank A, which is defined as n cross n matrix. Sorry, n cross n1. N cross n is to and rank of A n cross n is nothing. M cross n is m. Okay. Number of linearly independent rows or columns. Okay, so rank A does not depend, so our answer is rank A has nothing to do with its power. So whether it's a square or cube or anything, it will always be m. So option A is the correct answer. Option A is the correct answer. Okay, another question is from 2019 June. The operator A has a matrix representation 2, 1, 1, 2 in the basis spanned by 1, 0 and 0, 1. In another basis spanned by 1 by root 2, 1, 1 and 1 by root 2, 1 minus 1. The matrix representation of A is. Okay, so we know by similarity transformation, we can go from one basis of representation to another basis of representation. Okay, so by similarity transformation, what we have is, by similarity transformation, A is transformed from in one basis to another basis, right? So B equals to P inverse AP. P is a unitary matrix and A is the representation in the earlier basis. Okay, so whatever basis now we want, we will multiply with P. That is okay. Now we will do it. Then you will get to know what is P. P is x1, x2. x1 is this, x2 is this. So when we will put into this, what we will get? 1 upon root 2 1 1 1 minus 1. This is P. Now we have to find the inverse of P. Inverse of P is found out as adjoint of P by determinant of P. Now what is adjoint of P? Adjoint of P is you know that how it is calculated. Adjoint of P is minus 1, close this one, close this one, this one is first left, okay, and multiplied by minus 1 to the power that is the first one, so 1 to the power 1, so this will become 1 to the power 1, so this is minus 1. Another one, close this one and close this one, okay. Now what we will get, it is to be 1 minus 1. Again similarly by this becomes again two and 1, this is minus 1, and when we'll close this one, 2 and 2, it is 1. I will show you, this is 1. So A11 is the first input, so minus 1 to the power 1 plus 1, and when we close the first row and first column, this will become minus 1, okay. This is when we will close this one and the row 1 and this column and this row, what we get, what number is left, that is minus 1, okay. That's why it is minus 1. A12 is close first row and second column, that is this one. What we'll get is 1 is the number, and minus 1 to the power 1 plus 2, which is minus 1, okay. Similarly A21 minus 1 to the power 2 plus 1, and close the second row and first column, this is 1, so again it is minus 1. A22 is minus 1 to the power 2 plus 2, that is a even power, so this will be 1. And A22 means second row and second column, this becomes 1, so 1 is the number, okay. Okay, now we may proceed to another part. What is that? Adjoint P is this one, okay. Now P inverse will be given as, now we have to find out the what will be the determinant P. Determinant P will be, if you take out it is determinant P to be 1 is 1 minus of plus 1 upon root 2, that is 2 by root 2. 2 by root 2 means root 2, so this becomes 1 upon root 2, 1 1 minus 1, okay. Here it is. Another part is P inverse is this. Now what which representation we have to find? The operation A has a matrix representation 2 1 1 2 in the basis span by 1 0 and 0 1, okay. This is the operator. A has a matrix representation in the earlier basis. Now for a new basis, what we have to do is put it in this equation, P inverse AP. P inverse is given as 1 upon root 2, 1 1 1 minus 1. A is given as 2 1 1 2, again 1 upon root 2, 1 1 1 minus 1. This becomes 1 upon 2. Multiply these two first. What we'll get? 2 1 plus 1, 2 and 2 minus 1, 1 is 1 plus 2, 1 plus 2, 1 is 1 minus 2. So this becomes 3 1 3 minus 1, and this is 1 1 minus 1 1 upon 2. This becomes 1 is a 3 plus 3 1 is a 1 minus 1 3 minus 3 1 plus 1. That's 1 upon 2 6 0 0 2. So solution is 3 0 0 1. This is the required representation of B. So B will be 3 0 0 1. Another thing which one should notice is B is equals to P inverse AP, since it is being diagonalized. So B should be, first point is B should be property of B. One should remember, you can write it down and memorize it. Diagonal. It should be diagonal matrix. Another one is diagonal matrix will be equal to eigenvalues of A. Whatever will be the eigenvalues of B will be equals to whatever will be the diagonal matrix will be equals to eigenvalues of A. Whatever is the eigenvalue of A, B will have the same eigenvalues. Okay, so B and A have same eigenvalues, If we take out the 2 1 1 2 eigenvalues, say it will be 3 and 1 only. Okay, we can do it like this: 2 minus lambda square minus 1 is equals to 0. 2 minus lambda square equals to minus 1. When we will solve this, we will get 3 and 1 only. We will solve it. 2 is 4 minus plus lambda square minus 4 lambda minus 1 equals to 0, which is lambda square minus 4 lambda plus 3 is equals to 0. So lambda square minus 3 lambda minus 1 lambda plus 3 is equals to 0. This will become lambda minus 3 minus 1 lambda minus 3 is equals to 0. This becomes lambda equals to 3 and lambda equals to as told. Okay, another point is third point: determinant of A and B should be the same. Whatever is the determinant of the A, B will have the same determinant. Okay, we will have the same determinant. We have same determinant. That's why it is known as similarity transformation. Okay, and sum of diagonal elements must be same. Obvious, that is obvious. Sum of diagonal elements must be 0. Must be same. Okay, now next question. The elements of 3 cross 3 matrix A has product of its row column indices Aij is equals to Ij. The eigenvalues of A are. So what is Aij? Aij is equals to Ij. Since it is a 3 cross 3 matrix, so it will have 3 rows and 3 columns. So each has the formula of Ij. That is first column, that is all the components are given as A11, A12, A13, A21, A22, A23, A31, A32, A33. So we have to put in place of I and j to be 1 1, Ij is 1 2 and 1 3, similarly like this. So it will be 1 into 1, 1 into 2. It is a general representation. Okay, So these will be the quantities under the matrix. 2 into 3, 3 into 1, 3 into 2, 3 into 3. That is 1, 2, 3, 2, 4, 6, 3, 6, 9. Okay, so this is the required matrix A. Okay, now what is another eigenvalues of A are? Now to determine the eigenvalues, what we have is, we have already read the Cayley-Hamilton theorem. So what we do is, we always take the equation in the form of A minus lambda I, which means 1, 2, 3, 2, 4, 6, 3, 6, 9. This becomes minus lambda 0, 0, 0 lambda 0, 0, 0 lambda. This becomes 1 minus lambda 2, 3, 2, 4 minus lambda 6, 3, 6, 9 minus lambda. Now we will determine the eigenvalues. We are multiplying. 1 minus lambda is 4 minus lambda, 9 minus lambda, minus 36, minus 2, 9 minus lambda, minus 6 is 18. Okay, I hope I am correct. Next part 3, 6, 12 minus 3 of 4 minus lambda. This becomes as 1 minus lambda, 9 plus 36 minus 4 lambda minus 9 lambda plus lambda square minus 36 minus 2, 18 minus 2 lambda minus 18 plus 3, 12 minus 12 plus 3 lambda. This becomes 1 minus lambda, 36 cancels, lambda square minus 9 of 4 minus 13 lambda minus 18 cancels, plus 4 lambda, 12 cancels. This becomes 9 lambda, which must be equals to 0. A minus lambda I must be equals to 0. This is given. A minus lambda I determinant. A minus lambda. Okay, lambda is equals to 0. So this is all equals to 0. Now the equation becomes lambda square minus 13 lambda minus lambda cube minus plus 13 lambda square plus 13 lambda is equals to 0. 13 lambda cancels, minus lambda cube plus 14 lambda square is equals to 0. So lambda square gets common. This becomes minus lambda plus 14 is equals to 0. So lambda square is equals to 0, or lambda is equals to 14. So lambda square equals to 0 means lambda is 0, 0. Two factors are 0, 0 and 1 is 14. So eigenvalues are 14, 0, 0. Okay. So lambda 1 is 0, lambda 2 is 0, lambda 3 is 14. So eigenvalues are 0, 0 and 14, or 14, 0, 0 or 0, 14, 0, anything in any order. Now another question is from 2018 December. One of the eigenvalues of the matrix e to the power a is e small a, where a is a0, 0, 0, 0 a, 0 a 0. The product of the other two eigenvalues of e to the power a is. So basically, what is the eigenvalue of the matrix e to the power a is? If we take the determinant of e to the power a, what we know as determinant of any matrix is product of eigenvalues, okay, and trace of a is sum of the eigenvalues. Okay, remember this thing. So determinant of e to the power a is e lambda 1, e lambda 2, e to the power lambda 3. These are the three eigenvalues of the e to the power a, eigenvalues of e to the power a. So one of its eigenvalue is already given, that is e to the power a small a, e to the power small a, e to the power lambda 2, e to the power lambda 3. Now, so determinant of e to the power a, since base is common, what becomes a plus lambda 2 plus lambda 3. So this is what basically, this is basically the trace of the matrix A. Trace A. Determinant e to the power a is trace A. Trace A means trace A is lambda 1 plus lambda 2 plus lambda 3. One such element of lambda 1 eigenvalue is A. Okay, and another one is lambda 2 plus lambda 3. So it can be easily solved now. So now we have to determine the eigenvalues and other eigenvalues of matrix A. So how we will find? Again by the Hamilton theorem. This becomes a minus lambda I equals to 0. Okay, a minus lambda 0 0 0 0 minus lambda a 0 minus lambda is equals to 0. This becomes a minus lambda multiplied by minus lambda minus a square. Other parts are 0, so those won't be counted. A minus lambda, this becomes lambda square minus a square is equals to 0. So lambda is equals to a, or lambda square is equals to a square. So lambda is equals to a and lambda is equals to plus minus a. So we have three factors: lambda 1 equals to a, lambda 2 is equals to a, lambda 3 is equals to minus a. So we know already one is the one eigenvalue is already a, other two factors are a and minus a. So we will put in the trace a. Trace a is a plus lambda 2 plus lambda 3. This becomes a plus a minus a equals to a. So trace a is e to the power a only. A only. So determinant e to the power a, e to the power a becomes e to the power trace a, and trace a is found to be e to the power a. Okay, so from determinant e to the power a is already given to be this one, e to, okay. So this becomes e to the power a, e to the power lambda 2, e to the power lambda 3 equals to e to the power a. E to the power a, e to the power a cancels. This becomes e to the power lambda 2, e to the power lambda 3 equals to e to the power 0, which is 1. Okay. So here we see is the product of the other two eigenvalues of e to the power a. So other two eigenvalues are e to the power lambda 2, lambda 3. So their product is 1. So answer is 1. Option 4 is correct. Option 4 is correct. Okay. 2018 December now. Another question from 2018 December. A 4 cross 4 complex matrix A satisfies the relation A dagger A equals to 4, where I is the 4 cross 4 identity matrix. The number of independent real parameters of A is. So it is, since it is a complex matrix, so it is a 4 cross 4 matrix. That means A11, A21, A22, A31 and A41. Okay. So this becomes A12, A13, A14, and last terms become A44. This can be filled up. A22, A23, A24, A32, A33, A34, A41, A42, A43, A44. So there are total terms to be 4 cross 4 matrix. So total terms are 16, 4 square only. Okay, so total terms are 16. Now the real parameter, since it is a complex matrix, so A11 might be A plus IB of the form. It must be of the form this, since it is a complex matrix. So all terms can be composed of A plus IB. So total real parameters change to be total real parameters become, since it was 16, there are total number of 16 terms, but each one has two real parameters, that is A comma B. A and B are the two real parameters in each of the quantities, each of the digits, A11 and A12. So 16 into 2, it becomes 32. So total real parameters are 32. Okay, now the condition which and it says that A is a complex matrix which satisfies the relation this. So when we have A dagger, A is equals to 4I. So what this becomes as 4 0 0 0 0 4 0 0 0 0 4 0 0 0 0 4. So this is the matrix which so when we multiply A dagger and A, this gives us unit 4I, that is 4 multiplied to the unit matrix. Okay, now when we compare on the both side, that is LHS and the RHS, what we will have is, we will have 16 number of equations. 16 number of equations we will obtain. 16 number of equations are obtained after equating on both sides. Equating on both sides. So this means there are 16 number of constraints. 16 number of constraints. Okay, there are 16 number of constraints. So number of independent real parameters of A is, that means there are 16 number of constraints. So there, to find the independent real parameters, what we need is total number of real parameters minus number of the constraints on the real parameters. What are the constraints on the real parameters? There are 16 constraints on the real parameters. So in order to find the number of independent real parameters equals to total number of real parameters minus number of constraints on the real parameters, which is found to be 32. Total number of real parameters is 32, number of constraints is 16. This becomes this 16. So 16 is the answer, option 4. Now another question is from 2018 June. Which of the following statements is true for 3 cross 3 real orthogonal matrix with determinant to be +1? So for first option, the modulus of each of its eigenvalues need not be 1, but the product must be 1. So determinant is, we have already told, product of eigenvalues, and it is given to be 1. Determinant is already given to be 1. So this the modulus of each of its eigenvalues need not be 1, but the product must be 1. So option 1, modulus of each of its eigenvalues need not be 1, but the product must be 1. So for orthogonal matrix, determinant can be +1 and -1 both. So this must is the assertive part, which says that it must be 1. For real orthogonal matrix, determinant must be only +1. it can be -1 also. There is another possibility also. If it was written as to be, but the product must be 1 or -1, this option would have been correct. So this option is not correct. At least one of his eigenvalues is +1. So in order to have the determinant to be 1, it must have 1 multiplied to another other two eigenvalues. So at least one of his eigenvalues +1. This is right, and we can find it like this only. Suppose there are eigenvalues maybe either +1 or -1, or e to the power I theta, or e to the power minus I theta. When we multiply these two, what we get is 1 only. Okay, so there are possible combinations of eigenvalues like this: 1 1 -1 -1 1 e to the power I theta, e to the power minus I theta. So 1 is the constant eigenvalue, which should +1 is a constant eigenvalue. At least one of his eigenvalues +1 is true for our case. Next, all of his eigenvalues must be real. None of his eigenvalues need be real. So now, since it is given to be real orthogonal matrix, so we cannot predict what can be the eigenvalues. It depends what when we will find it. We don't know what it will turn out to be. What will be the eigenvalues? Okay, so only thing we know is determinant of the real orthogonal matrix should be equals to 1. This is the only condition which is given. So we don't know what can be the all of its eigenvalues must be real, or there are, you can see these options: first, second, and third. First as all the eigenvalues must be real, all are real, but in this case it is not real. So these two are not correct. So only correct option is option 2. So our next question is from 2017 December. Consider the matrix equation 1 1 1 1 2 3 and 2b 2c x y z multiplied to x y z 0 0 0. The condition for existence of a non-trivial solution and the corresponding normalized solution up to a sign is this one. So for existence of non-trivial solution, rank A, if it is A, if it is x, this is equals to b. So ax multiplied equals to b. 1 1 1 1 2 3 2b 2c. This becomes 0. When we will solve this become 1 4c minus 3b minus 1 2c minus 6 plus 1 b minus 4 equals to 0. 4c minus 3b minus 2c plus 6 plus b minus 4 is equals to 0. This becomes 2c minus 2b plus 2 is equals to 0. C minus b plus 1 is equals to 0. B minus c is equals to 1. So b is equals to c plus 1. Okay, now for trivial solution, x must be 0 when A inverse exists. Okay, A inverse exists when this determinant A is not equals to 0 when A inverse exists. Okay, now for non-trivial solution it is x not equals to 0, which means A inverse does not exist. So for A inverse to not exist, one should have determinant A equals to 0. This is the case. Determinant A equals to 0. That's why we have got B is equals to C plus 1. Now we will say B is equals to C plus 1 is the option 4 is the correct answer. So next question is from 2017 June. Which of the following cannot be eigenvalues of a real 3x3 matrix? So for the eigenvalues of the in order to determine the eigenvalues of the real matrix, one should have remembered this thing. For a real matrix, well, first thing is determinant is real. Second thing is trace is also real. So we will determine for all these options what is the determinant. Lambda 1, lambda 2, lambda 3 multiplied trace is the sum of the eigenvalues. So these are the eigenvalues given. So for the first option, this become 2i multiplied by minus 2i. This becomes 4. Trace is 0. Second, it shows that both are real. First option is correct. Again, determinant is 1. Trace is 3. Again, second option is also correct. First option is also correct. Third option, e to the power I theta multiplied by this becomes 1. This becomes e to the power I theta, that means cos theta plus I sin theta. Cos theta plus I sin theta, we will open it. Another one is cos theta minus I sin theta plus 1. This becomes 2 cos theta plus 1. Again, it is a real one. Now the last option, fourth, determinant is some multiplication of these eigenvalues, that is 0, and sum will be 1 plus I. So it is not real. So this is complex. So fourth option is not correct. Okay. Now last question of the matrices topic. The matrix M1 3 2 3 minus 1 0 0 0 1 satisfies the equation. Now we just have to apply the Cayley-Hamilton theorem. What we have to do is m minus determinant of m minus lambda I is equals to 0. So this becomes 1 minus lambda 3 2 3 minus 1 minus lambda 0 0 0 1 minus lambda is equals to 0. We have to find this only. Minus lambda multiplied by minus 1 minus lambda 1 minus lambda minus 0 minus 3 3 of 1 minus lambda, okay, minus 0 plus 2 0 minus 0 0. So 1 minus lambda is minus of 1 plus lambda and 1 minus lambda 9. 1 minus lambda is equals to 0. So 1 minus lambda, when we take out to be common, this becomes minus 1 minus lambda square minus 9 is equals to 0. This becomes, take out the minus 1 minus lambda equals to lambda square, don't take out minus, put it inside, that becomes lambda square minus 1 minus 9 is equals to 0. Lambda square minus 10 and 1 minus lambda is equals to 0. So this becomes, we have to solve this too also. Lambda square minus 10 minus lambda cube plus 10 lambda. Now instead of lambda, lambda must satisfy its characteristic equation. M must satisfy its characteristic equation. This is the characteristic equation. Okay, when it is in the form of lambda, it is the characteristic equation. When m minus lambda I determinant is equals to 0, this gives the characteristic equation. So m must satisfy its characteristic equation. So what we have is minus lambda cube plus lambda square plus 10 lambda minus 10 is equals to 0. Take the opposite one, lambda cube minus lambda square minus 10 lambda plus 10 is equals to 0. So m must satisfy its characteristic equation. This gives to be m cube minus m square minus 10m plus 10I is equals to 0. So correct option is m cube minus m square minus 10m plus 10I. This is option third. Option 3 is the correct answer. Okay, thank you and take care. Other topic will be the ordinary differential equation. Hope to see you again.